All right, so here in this video lesson, we are going to investigate how we can apply our ability to take derivative into solving an equation. So before we actually get any further, I am not going to really rush into introducing the title of our discussion topic here, but as I just now said, we are going to apply our ability in taking derivative into solving an equation. So the work seems surprisingly simple, but here's the thing. Up to this point in your calculus learning, we have only learned if we are given a what's so-called a linear equation, generally speaking, ax plus b, and set the opposite side equal to 0 like that. This is a linear equation. Then the answer is a definite sort of like a quick formula. As we grow more mature into our mathematical learning, then solving a linear equation pretty much sets into a formula. So finding the x value satisfying this equation, this linear equation, is simply to be just minus b over a. Okay, and that's how we solve a linear equation. And so this quick formula here gives us the solution, the value of x that satisfies the left-hand side of this equation to equal the right-hand side. And then when we advance to a little higher level of math, then we came to, and allow me to switch quickly to the other board. When we advance to the higher level of math, and we came to an ax squared plus bx plus c, and this is famously known as the quadratic equation. Okay, and this is where we started to be introduced. We started to be introduced to the quadratic formula, which was minus b plus and minus the square root of b squared minus 4ac over 2a. But so now really the linear equation, as I have mentioned, and the quadratic equation just now, those are the only two equations that we really have a solid formula, a definite formula to find a solution. So if we follow this formula here, we will be able to find the values, the value or the values of x that are satisfying the left-hand side equal to the right-hand side in a quadratic equation like that. So now back to what I was in the middle of saying earlier. At this point in our learning, and pretty much that's the way how it is for most of the mathematical problems out there, for most of the solving equation problems out there, we only know a definite formula for either a quadratic equation or a linear equation. So if we step out of this world of solving quadratic equation and linear equation, then say, for example, if we step into something like this, cubic x cubed minus 3x plus 1, for example, equals 0. This all sudden brings us into an entire brand new world which we has almost no clue about. Okay, because now, so my point is that solving these equations other than solving these equations other than the quadratic or the linear equations has always been a very challenging work. We have never had any, and to be honest, we have never had any any definite method how to handle these kind of equations. And the world of solving equations out there are not limited to just these polynomials equal to 0. We also have these kind of equations, say e to the x equals x. How can we find a value of x that satisfies e to the x equals x? We can have solve an equation so that natural log of x equals x. And so we have a lot of equations out there to solve where we never had a definite solution, a definite method to solve. And so that's why when it becomes challenge, to find a definite method to solve, then we're going to start looking into some numerical methods. The idea now is that we are going to approximate the solution. So any equation in the end, say an ax plus b x plus c equals 0. It's a quadratic, that's how we call it. An ax plus b equals 0. Or something complicated as an x cubed minus 3x squared or minus 3x plus 1 that I brought up on the other board earlier. Any of these, once we successfully put all the terms into one side and leaving a 0 on the opposite side, we can regard all of these as some function. So I can see this as some function. I can see this as another function, g of x. So the ax squared plus bx plus c can be seen as an f of x. And then the ax plus b can be seen as another function, g of x. And then the x cubed minus 3x plus 1 here can be seen as another function. So generally speaking, my point here is that solving any equation here is basically bringing ourselves to the question where find the value of x such that a particular recognized or given function will equal a 0. Okay, so that's what it means by solving an equation. We solve an equation in a setup that we recognize some function f of x on the left hand side to equals x, and we want to find the value of x. Okay, that satisfies this equality, and that's what generally solving an equation means. And so graphically speaking, that means at some point our graph f of x will give us a graph. So finding 0 or solving for x satisfying f of x equals 0 means we're looking for those, one way you can say the x-intercept, or these are zeros. Okay, these are zeros because these are the x values that cause the function to equal 0. That's one way of saying that, or we can also call these the x-intercept. There are so many ways of calling these. Okay, we can also refer to those as x-intercept, and sometimes these are also being referred to as roots. Okay, so that's roots. You can call it x-intercept. You can call it 0, or you can also call that solutions. Okay, so the solution is just the sort of like the most the general way of calling it. But basically, we're looking for the x values. There could be more than one places on the x-axis here where the graph crosses the x-axis. Okay, and that's what we're trying to look for. But so now back to what I was saying earlier. Since we're now facing a big challenge about finding a particular method, finding a good definite particular method to track down and find the exact values of all these zeros or these roots right here, then we're going to turn our focus to using some numerical methods. Meaning, we're going to start out, what I mean by turning over to a numerical method here means we're going to find a way to say, I know that our function here crossed the x-axis at some point there, but let's say, how can we come up to something that's close enough, some value of the solution that's close enough. Okay, and that's what it means by some numerical methods right here. We can only approximate. And it makes sense that a lot of time when you see even when we have a quadratic ax squared plus bx plus c and using a quadratic formula, minus b plus and minus square root of b squared minus 4ac over 2a. Even this formula, a lot of times a formula like this gives us a very, inexact expression, and we have to leave that as an expression. But getting a real numerical answer for something like this is also quite challenging. So the idea now is that how can we get the best approximate to the actual solution of our equation. Okay? And so what I'm about to introduce now here is among so many different numerical methods, so many different approximation methods out there, we are now going to learn. So we are now going to learn about the Newton's method. And I'm only saying that this method is just one method, one approximation method among so many different methods out there that So the other methods, you're going to have to wait until a more advanced course in mathematics, or there's actually an entire field in numerical mathematics, right there, in the kind of mathematics that we approximate a value. Okay, but Newton's method is the one that's easy enough that can be brought in and taught at a beginning calculus course level, right there. Okay, so just keep in mind, our goal now is that there's a function, and the function will cross the x-axis at some point, and we are going to learn about this method, that's so-called the Newton's method, to approximate, to come up with a value close enough to the actual value, to the actual solution of this. So this is f of x, and this point right there means f of x equals 0. We want to find, at least if we cannot come up to a finite method to find the actual value here on the x-axis that satisfy f of x equals 0, then we're going to come up with a numerical approximation of that. Okay, and even though before we really start into this journey, even though we are about to learn the method, and we will learn most of the method, but there are still a lot of details out there that are impossible to be taught at this beginning calculus level. And so if any of you are certain after learning through this lesson right here and have a feeling that you have a good passion for this kind of method right here, then I highly recommend that you take a higher course and eventually navigate yourself into a direction where you will study specifically about numerical methods. Then there you will have, your professors there will be teaching in much more details about the weaknesses and the advantages of the Newton's method. So here in this lesson, I can only, for the viewers being tentatively at calculus, the beginning calculus level, I can only introduce just how the method's going to be ran, how the method's going to be used. Okay, but I won't be able to cover all of those details in terms of weaknesses and advantages out there, and how to improve and make the method to work better. Those will be saved for the much higher and later courses in your career. Okay. All right, but so now the reason this method is being introduced at a calculus course, because this is where I see this is also another application of where you apply your ability of taking a derivative into solving an equation like that, just like how I explained in the beginning of our the video here. Okay, so really, let's get to work right here. And just for you to know as well, so the Newton's method is also being referred to as the Newton-Raphson. Let me make sure I double check and the Newton-Raphson methods, because really it's not only Newton that came up with this method, but there were actually two men who came up with this method right here. Okay, all right, but now let's beginning with an introductory problem right here. I am going to get into. So let's say we are given this function here, f of x is to be x to the fourth minus 4x cubed plus 1. Okay, and so now, right at the moment that I'm introducing this function, let me quickly show you the graph of this function, and you will understand what I mean immediately. All right, so my screen now is ready, so let's go ahead and have a look at that. So this is our graph for x to the fourth minus 4x cubed plus 1, just as how I wrote on the board right there. Okay, so now just immediately looking at the graph, and even though I'm showing the graph here, I have to admit the whole point of this method is to be able to solve without relying too much on the graph. Okay, and that's the good thing about this method right there. So for first time being introduced to for anyone being the first time being introduced to the kind of problem, then I show the graph. for you to understand what is going on. But the main aim of this problem, this kind of method, is not is supposed to be for people to be able to solve these or approximate the solution of these functions without without seeing the graphs. Okay, and so now back on the graph of this function. This is the graph for x to the fourth minus 4x cubed plus 1. And so now the graph tells immediately, and I purposely hide away all the the values 1, 2, and 3, and 4, and basically the numerical scaling on this axis right here. All we know is that graphically speaking, this graph crosses at some point here. So there should be one solution where f of x equals 0, and there should be another one, graphically speaking. Okay, so there should be two values. So we want to approximate. So how about my aim here? Let's approximate this value here, this lower value of of the solution. So this graph, when we set it equal to 0, this function, when we set it equal to 0, then we're gonna turn out having two solutions. Let's now focus on approximates that value there. Okay, so let me quickly zoom that in. Okay, and so like I said, I purposely hide away all the the numerical scaling like 1, 2, and 3, and so on, because I want you to just only have an idea that, hey, the graph has that nature. It crosses the x-axis twice. Let's approximate those, because even if we have the scaling, it's not gonna be useful in terms of approximating in terms of finding out where those values are. Okay, and so now let's get back to work here. So now the idea, our goal here is to approximate. Okay, to approximate the solution. Okay, of f of x equals 0. So this is our f of x, and we want to approximate. And as I have always shown in the graph right here, then there are two solutions. So how about to be precise right here? So as far as the solution, I'm gonna put a note right here. I'm going to open a parentheses. How about the lower value? Okay, the lower value, because we have seen through observations on the graph that there are two solutions, two x values where the graph crosses the x-axis. So I'm here just aiming at the lower value. All right, and that's our goal right there. And so we want to approximate that lower value solution of this equation. The equation that, so namely speaking, it's x to the fourth minus 4x cubed plus 1 equals 0. This equation right here, we want to approximate the lower value of the smaller solution. Okay, all right, so here's the plan. So of course our function is f of x is equal to x to the fourth minus 4x cubed plus 1. Okay, and so the method I'm about to introduce here requires us to have the derivative of this function here available. And another thing I have to point out, you can only, when we actually get into an example or any of the actual problem, you got to make sure that you can only call that f of x when you have turned your opposite side of the equation into a complete 0. So I'm talking about if we have something like this. If we have something like this, x to the fourth minus 4x cubed equals -1. We don't call that f of x. This is not quite to be regarded as f of x, because we want to rewrite our equation in a form that everything is on the left hand side. I mean, everything, all the non-zero terms are on one side, and the opposite side is nothing but just a 0. And that's the whole idea, that we want our f of x is to equal 0. Okay, so even if you have an equation that started out some non-zero, some on both sides, and we have to make sure that to turn your bring your terms all over the equation so that you have a 0 on one side, and then the other side will be regarded as your function. And so now once we have successfully landed into that left hand side being completely a function and the right hand side is a 0, then we're going to go ahead and back to what I was saying earlier, the methods we're about to learn here requires us to have the derivative of our function available. And so now at this point, anyone arriving at this video should be fluent in terms of taking these easy enough derivatives. So this should be giving me 4x cubed minus 12x squared. There's no there's no need to factor out or simplify or anything like that. It's just when we get that derivative, that's here. We got the derivative. Okay. So now here's the whole idea of the solving work here. So now I'm going to get back to the graph, and this is what I'm going to be doing. So even though I set all right, so give me 1 second to quickly adjust my graph right here. Okay, so now even though I said I purposely hide away, but now it's time for anyone to see it anyway. So now with the actual numerical scaling of our graph being displayed right here, then you can see that this lower value of our solution, the one that we're aiming at right now to approximate, is somewhere between 0 and 1, and it's just about barely past halfway between 0 and 1. So it's somewhere just past halfway, so somewhere higher than 0.5. So that kind of gives you an idea. So here's the hope, and it seems like it's closest to x equals 1 on the x-axis. Okay, and now I'm going to get back to the work. So now I am going to, let's start out with, let me switch to my other board. So this method we're about to learn always requires to have a chosen starting point. So I picked this value. You can pick something else different. Okay, but how about I'm going to choose a starting point to be 1. So you got to understand, this is only a starting point, and definitely f at 1, x to the 4th minus 3x, x to the 4th minus 4x cubed plus 1 is not equal to 0. But from there, we're going to come up with a method to produce the later ones, the later values that come up closer. And so I will explain all of that in details. But so clearly, x equals 0 is not, x of 0 equals 1 is not the solution to this equation. But now, here's what I'm saying. I am going to find another value that's closer to the actual value by doing this. I'm going to call that now x of 1 right here. Okay? And x of 1 now, I'm going to be done by doing this. I'm going to find x of 1. Supposedly, x of 1 needs to be closer, and you already seen that through the graph. You have already seen that through the graph that our actual 0, our actual root of this equation here is somewhere less than 1. So we chose x equals 1 to be the starting point here. So x1 tentatively or purposely, I need to be, at least if it's not hitting right on spot, then it has to be somewhere closer to the actual value. So that's what I'm intending for. Okay, and so now I'm going to offer a formula. This formula is as following. x1 can be calculated from our previous starting point right there, x of 0. I am going to go x1 equals x of 0, subtract a fraction that goes f at x of 0 over f prime at x of 0. Okay, and ladies and gentlemen, this is the main core method of what Newton's method is all about. And once we will be done with a couple of steps right here, then I will make a generalize of this formula I'm doing. Okay, but so hey, x of 0, we have already chosen that. X equals 1. So this formula here is nothing but just 1 minus f of 1 divided by f prime of 1. Okay, so I can leave that for my viewers to do a calculation here. Okay, because this is straightforward enough that you can quickly do that on any basic calculator. So of course, if your calculator is too basic, then it takes longer time. But be patient. Numerical methods, any numerical method is always a time consuming, but because it's worth, and it's because we're in the desperate situation that we have to use it. So that's the only choice for us. So no matter how long it takes, if we really have to find a solution of something like that, we have to go through the calculation methods like that. So it could take long. And so now I'm going to spend a minute to quickly calculate my value right here. So now my calculation shows, and of course I just simply use this pretty straightforward formula. I came down to 0.75 is my x1. Okay, I came down to 0.75 being my x1. So let me quickly graphically show what's going on. All right, so again, back to my graph like that. So if we follow with the methods, then this is the point that we're looking at right here. You see our first point that we chose is here on the x-axis. That's why now all of a sudden anyone viewing this video will see that I have right here on the x-axis, x equals 1 right there. Okay, that's that point popped out, but that was only our starting point, and it was of course quite a way, okay, being off from this actual solution. But now x1 after calculation, this new point right here is x1. So in coordinates value on this line of values right here, then it's 0.75 comma 0. But how it is now, it's from our starting point x0 equals 1. Now we came to another value that we call x1, but which is graphically speaking a lot closer to this solution already. Okay, and so now, but see, there's still a little bit of difference between the actual solution and our x1 value. So we're not happy with that point yet. And so that's why now I am going to head out for x2. So now x2 here again. So supposedly or tentatively, x2 needs to be closer to that root, to that 0 point on the x-axis that you have seen in the graph earlier. So that means now, the reason I said that is because it's a way for us to check that, but we are going to use the exact same or the very similar setup right here. So let's have a general look right here. When we calculate it, of course, x sub 0 was given, but when we start calculating x1, the one step away, right after our chosen one right there, then we went with the very preceding ones, x sub 0. So here's x1, and then the formula relies on x sub 0 minus f of x sub 0 over f prime of x sub 0. So think about it, and we came down to successfully calculated x1. So now if we want to find x2 tentatively closer to the actual root right there of the equation, then x2 needs to be done using the similar setup. I'm not going to go with x sub 0 here, but it's x1 right there because we already calculated and had the value for x1 available. So now it's x1 minus f of x1. So the entire formula now has x sub 1 substituted in over f prime of x1. And keep in mind that now we have a known value for x1. And so I'm going to go ahead and use this value x1, substitute it, and substitute that into our setup of the formula. And now I'm ready for some work again. So writing it down, it's actually 0.75 for x1 minus f at 0.75 and divided by f prime at 0.75. Okay. And then quickly, before I step away for my quick calculation, this is the reason why I was saying earlier before we get started into the problem. This method requires us to apply our ability in taking a derivative, because it's here. It's being part of our formula for the approximation. Okay. So now I am again going to step away shortly for a calculation of my x2 value, and viewers are invited to do the same thing at the same time with me. It's going to be a very lengthy value on my calculation, but I decide to keep it all, at least whichever the calculator I'm using, the technology I'm using. I keep all that precision being displayed here from my calculator so that you can see what's going on. Okay, so my calculation shows, and I might have to hop back and forth quite a couple times here. So my x2 value is 0.669. I mean 67669. And a lot longer. Seven, 5, 3, 0, 6, 8, 4. Okay, so at least that's the precision that my calculator was able to give me in a pretty lengthy calculation. And I actually double checked, and this is supposedly the very last, the very 3 ending digits so far is 864 instead of 684. 864. Okay. All right. So this is my x2, and you can see that we started out picking up x of 0 equals 1, and it was, of course, the picture was telling it was quite away from being noticeably off from the actual root of our equation. And we came to x1, and x1 already came to somewhere closer because x1 was 0.75 on the x-axis. So this is x2, okay? This is x2. And so now let me once again graphically put up that display right there. Okay, so my x2 is here. All right, so you can see that now in this zoom level of mine, then we almost cannot tell the difference between where the graph in red here crosses the x-axis and where we place that point. So the point in black here is meant to be our x2 value on the x-axis. But you know, from this zoom level, then we are not able to tell much about the difference between the black point and the point where this graph crosses the x-axis. So let me zoom it in even a little further. So now we're gonna start seeing. Now we're gonna start seeing some actual difference, slightly difference, right? Some slight difference between. So x equals 1 is our value right here. We chose as start. So that's value right there is our starting point, and this is our x1. Okay, and that was of course x of 0. And now this is our x2. Already came pretty close. I had to put in some really close zoom right there to see some difference. Okay, and so now, but in case I'm not happy, and maybe in case any viewers is still not happy with this slight, even though so slight difference, then we can go even further. So now, back on my board, I was doing my work. Then I must erase some of the work here, and I'm going to write it down and just simply record as records here. So on records, we already found this is our start. That was our start. And we came down to x of 1 being 0.75. Okay? And so just now, my x of 2, I'm recording it down. That's part of my recording work right here, 0.66, I mean 67. So 0.67, 669. 7530864. Okay, a very lengthy value, but it's working. And so now, if anyone is not satisfied with x2 right here, then we can even go further. Okay, and so x3, you have seen this formula twice. So x3 here is going to be, I'm going to look back at the most recent one, x2. Okay, so x3 now is going to be x2 subtract f of x2 over f prime of x2. And that's it. So this is the third time we are seeing this formula. So I believe that any viewer who's following along with this video lesson is starting to click with the generality of this formula. It shouldn't be too complicated to recognize. Okay? And the idea now is that, see, x sub 0 is our start, but x1 is closer to the solution, and x2 is even closer to the solution, and x3 is even closer tentatively, and that's the idea. Okay, and so we write these values here as, you know, as successive values that keep getting closer to the actual solution. So it's a sequence of values here in the end. I recognize it. All right, so the values here for x2 is pretty lengthy, so I'm not even going to be able to write it on the board here. It's too long for us. Or maybe I'll just write it down, but I have to chop up a lot of values there. So how about 0.67669, okay, and a lot longer means I don't even round. I just have to leave it like that. Minus, and now f at 0.67669 and a lot longer. Okay, that's not really rounded properly. It's just I'm just hiding the other digits, and then divided by f prime at 0.67669 and a lot longer. Okay, and so now those standard TI-8384 calculators has a really nice feature that you can store your, no matter how lengthy your value is, but you can store your exact answer there and then retrieve that and use from its own internal memory. So you can start making use of that. Sadly, I'm not going to be able to show that as part of our video lesson here, but you should be able to operate with your calculator there. But so now I am going to step away again and to come up with the actual final value for x3 here after our calculation. Okay, and the TI-8384 calculators are on standard the pretty useful one, but those are not the only one that you can use. You can even use with the very basic calculators that will help you to do your work as well. All right, so and again I might have to hop back and forth a couple times. So my value turns out to be, for x3, it's 0.6696 944 75 874, and a lot longer. All right, and so another lengthy value, and you can see that it's not being that much far away at all from x2 right there. Okay, but this is our x3. This is our x3, and so now again, let me quickly put that on the picture of our graph right here together with our graph. So this is our graph again. And x3 is right here, and just now I popped out another point popped out, and even with this quite extreme level of zoom right here, then we still can't tell the difference. It looks almost like this x3 value is right on the graph where it hits with the x-axis, but it's not, because right here, as I keep now zooming in, we're going to start noticing some difference. Okay, as I keep, see, now it's going to start generating some difference right there. Okay, but trust me, eventually even technology will fail to keep showing the differences. So, you know, even any technology has a limitation, but the method here tentatively leading us. The methods will keep leading us into the closer and closer solution. Okay, and so for this introduction problem right here, I am going to stop at x3 over here. So the whole idea is just, you know, if I'm still not happy with this value, then I'm going to go further for x4, and if I'm not happy with x4, I'm going to go further with x5 and something like that, and for all that. Okay, so that's the whole idea. So now let me get back to my earlier board right there and point out what formula was the main formula being used right there. So now, provided that you already understood well enough what our goal is, and provided also that you already found the derivative of your function, then to approximate this value, then the whole idea is to start, okay, start with a chosen x sub 0 value, okay, and I have to put a note with, even though right now it's quite unclear, closing up, okay, close enough to the actual solution. And then from that point on, then for any of the later steps where I namely call that, how about x sub n plus 1, like this, at any n sub 1 step, I am going to calculate the approximation at the n sub 1 step by using the nth step. So if you got an x sub 0, then you can use x1 can be calculated as this formula. That's what I meant like this. So x sub 0 means n equals 0. But generally speaking, the x of n plus 1 step is always going to be x at the x of n, or the nth step right here, minus the ratio of f of x of n over f prime at x of n. Okay, so ladies and gentlemen, this is just that famous Newton formula right there. That famous the formula that runs behind the scene in all of our steps so far in this what's so-called the Newton's method. Okay, and so the further we keep going, right, the closer it's going to be. That's tentatively the idea right there. The further we keep going, because we keep repeating this on, so if you got x sub 0, not happy with that, okay, then we go with x1, not happy with how close x1 is, we're going to go with x2, okay, and that's all that idea right there. Okay, so that's the whole picture of how it happens. So now allow me to really explain how did all this formula come from before we get into some actual example. So we now learn how it's run, but I need to explain where that formula came from and what was the philosophy, or what was the fundamental behind the scenes here that came up with this, that derived, that people came up with this formula right here. Okay, so now let me quickly turn into a different graph right here. All right, so now we're looking at a different graph. So here's the thing, see? So don't worry about what function that is. It's just some graph. It has some value right here. I mean some graph f of x, and it has some x value. That's what I meant earlier. It has some x values that at where the graph crosses with the x-axis. Okay, and unfortunately we, and here again I don't really need to put on any of those numerical scaling of our x-axis here. So that's just where our root is, and unfortunately this kind of graph is not easy. We don't have any definite method to solve. And so now here's the idea. The whole idea of Newton method is, first it has to be like this. Yes, we pick a starting out point. Okay, so this point that just now popped out is called a starting point, and of course graphically speaking it's quite a way. Doesn't matter how far close zoom or how far zoom that is, but it still makes some difference with the actual root or with the actual solutions of our equation f of x equals 0. So f of x equals 0 is right here. So if we can find that x, it's right there. But this is for sure quite far away. But now here's the thing. If once we pick that starting point, so I call this a starting point, I chose that point, and so once we have chosen that starting point, from where the starting point is on the x-axis, now that starting point will become, when we actually substitute that starting point into the function, then we produce this point right here, and this point is what? X of 0 comma f at x of 0. Okay, so now allow me to also make another hand sketch version on my board right here. All right, so with that sketch that everyone has already seen on the computer screen, then with a graph like that, see, we pick some x of 0. And so this point right there, that's what I meant. That point is generally x of 0 is the x coordinates, and the height, how high that is, f of x of 0. That's the coordinates point of this actual point on the graph, and that's how I had it. Even so, Desmos I'm using is still limited in terms of being able to display a general description like that, but we'll survive with what we have. We'll live with what we have. So now that's x of 0 comma f of x of 0. But now the idea is, the real idea now that was brilliant behind the scenes here, is that from this point we are going to, it's easy now for any calculus student to find the tangent line, the equation of a tangent line. So right there, think about if we shoot out a tangent line tangent to this red graph right at that point x sub 0 comma f of x sub 0. Then here's the thing, the tangent line itself as an equation, as a function, will also crosses the x-axis at somewhere. And so now that point where the tangent line crosses the x-axis is already closer to the actual solution. So now let me just graphically display the point right there. Okay, so this is where this point that I just now popped out is the point where the tangent line at x sub 0 on the graph is now hits the x-axis, and that point right there, now I can use that as x1. But so now let's slow it down a little bit, and I'm going to return to my writing board here, and let's do some quick little calculation. So quickly on the other board, in the way how I'm seeing, so just like how the graphical display was indicating, then at this point x of 0 comma f of x of 0, we are going to shoot out a tangent line, and that tangent line is hitting here as x1. And so here's the thing, I need more space to write all that situation. So after anyone is having a close observation of that, I'm going to switch back to my other board, and this is the calculation for that. The idea now is that at that point x of 0 comma y is f of x of 0 sub 0 comma f of x of 0, then the slope of the tangent line is f prime at x of 0. Okay, that's the slope. And then and I'm still using that very friendly mt value, like the slope of our tangent line at x of 0 on whatever curve that is. And so now putting it all together into as an equation, and think about it, your equation here is y minus, and again let me remind anyone, this point is the tangent point. I call that it's a tangent point, and it's a point on the graph and also on the tangent line. So to get the equation of a tangent line, I can also use that tangent point, and I'm starting out with the point slope equation. I mean, a lot of time throughout other video lessons, I'm not using too much of the point slope, but point slope equation can also be convenient a lot of times. And so here in this particular case right here, it's easy to help me that. So the point slope equation of our tangent line there is y minus f of x of 0. Okay, because this is the y value for our tangent point at x of 0, and that equals the slope. But now let me write directly the slope here of the tangent line is f prime at x of 0, and then we're going to multiply the slope of the line with x. So x and y, they're just the standard variables of our equation of the tangent line. But now x minus x of 0 here, that's the x coordinates of our tangent points, okay, which is also on the line itself, on the tangent line itself. So now from this one right here, then I can easily rewrite my equation into the standard y, the slope-intercept form. So this gives me the f prime of x of 0 multiplied with x minus x of 0 plus f of x of 0 on the other hand right there. Okay, and so now in that way, and then distributing that term right here into each term. So now we're looking at y equals mx sub 0, I mean f prime at x sub 0 times x. Okay, that's slope times x minus, and now f prime of x sub 0 times x sub 0. This is a value, it's a constant value. Okay, and plus with our f of x of 0. So these are all values. These are actual constant terms here that they are technically like terms. Okay, so slope, all that here is intercept. Okay, but now this tangent line need to, again, on the picture right there, on the picture, this tangent line, that's what the equation I just had on the board, need to hit y equals 0, because that's where it crosses with the x-axis. So y equals 0. Y equals 0 means I'm going to set this y value equals 0. And so setting that y value equals 0, I'm looking at now 0 equals f prime at x of 0 times x, and minus f prime at x of 0 times x of 0. This is an actual value right here, plus f at x of 0. Okay, I hope and as I said many times in other videos, feel free to pause the video if you need time to catch up with any of my steps here. Okay, so what I'm doing now is, because the plan here is that we want to find the x value where this tangent line of ours right here crosses the x-axis. And if it's at this point, if it's a little confusing to see our equation of tangent line, this is the mt right here. This is mt, and all that here is the plus b. Okay, so mtx plus b. The plus b part is right there. Okay, and so when we arrive at this equation, f prime of x of 0 times x minus f prime at x of 0 times x of 0 plus all that here, such and such, then in my next step of this equation, solving for x, then we're looking at what? It's easy. It turns out easily that we're looking at f prime at x of 0 times x of 0, okay, minus f of x of 0. And we're dividing all that there by f prime at x of 0 to equals x, okay, by just simply rearranging our equation, okay, by simply rearranging. And so think of this. We can algebraically break that down into two terms right here. So with that term right here, the subtraction signs there, we got two separate terms. So the first term becomes just simply x sub 0, because all that's here cancel out. The f prime of x sub 0 gives me just simply x sub 0, and then minus. But these two terms now, when we separate it out and put that over the common denominator, they cannot be canceled. So we're leaving that here as f of x sub 0 over f prime of x sub 0. Does that now look familiar? Okay, and so this value here equals x. So now I'm saying that this x value solved by this thing right here is going to be where this x value is where our tangent line at x sub 0 crosses with the x-axis. And now that new x value, we now call that x1. That new x value. Okay, and so that's the whole reason why I'm writing my formula a little bit backwards right here, but that's how I introduced earlier. We got x sub 1 equals x sub 0 minus f of x sub 0 divided by f prime at x sub 0. Okay, and so that's how we come up with x1. And so we can repeat the math here for x2, x3, because so again, look on the picture here. All right, so now once we come down to x1 right here, then again, if we want to get a closer value, to this actual destination of ours right here, then here's the next thing that we're doing. From where our x1 value is, think about if we substitute that into the actual function, okay, and now use that point, that actual point on our function here, on our graph here, as the new tangent point, okay, the tangent point at x1. I'm spelling it out hopefully clearly enough. But so now from that new tangent point here, I'm going to now put up the tangent line here. This is the tangent line at x1 right here. Okay, and so the tangent line at x1 now crosses the x-axis as another value that's now the picture is showing is a much closer value, right, on the x-axis. This is the tangent line at x1 right here. And hopefully you can all see that clear enough on the screen. All right, and that's why now this new point right there is where our tangent line at x1 is crossing with the x-axis. And so now we can call it, if this was x of 0 start, x1's here, now we can call it x2 on the x-axis. And so of course, if we follow through the math again, to follow through the quick deriving work similar to what I have done, then of course that's why we can again quickly and feel free to pause the video if you have to, and you can independently derive this on your own, but x2 should again arrive at x1 minus f of x1 over f prime of x1. And that's how, so I show the work deriving x1 from x of 0 and how we came to that. And so you can do the same on your own, try right there. I highly recommend you can try, and the work is simple enough. So x2 will be for sure equal to x1 minus f of x1 over f prime of x1 right there. Okay, and so that's this here is the value where the tangent line at x1 crosses with the x-axis, and the picture already showed that it's a lot closer to the actual value. And that's how in general at any next step, that's I call x of n plus 1 right there, it is going to be the very previous step, x of n minus f of x of n over f prime at x of n. And again, that was the formula I introduced earlier, and we used that throughout the entire problem. Okay, and so that's how it is for the formula. And now I just now show a brief proof of how it came about. Okay, so now we will be getting into some examples, and along with the examples I should be able to point out more details, even though, as I said again, up to this point there are still a lot of mysteries. And any instructor teaching a beginning calculus course should only be able to have some kind of expectation that's only moderate enough for calculus students at the beginning level right there. And so and just like any other professors teaching calculus 1 or introductory calculus, then we won't be able to cover too much or that much details about this method, because you guys, any student, need to understand a lot more understanding, a lot more advanced understanding to completely unlock everything about this method, this Newton's method. So we only about just stuff as how we can get it done. And a lot of times the instructor have to provide and a lot of time instructor have to be generous for the students in terms of how to apply this problem, and you will understand what I mean by that.